Periodic motion, question 8. The diagram shows how kinetic energy of an oscillating mass varies with time. And you're told that we're considering simple harmonic motion. First part, you're asked to find the frequency of the oscillations of the mass. Now you cannot read frequency directly from a graph of energy against time, but you can read the time period from this graph. However, be careful. This graph is plotting kinetic energy against time. It is not displacement against time. You are looking to identify the time for one complete oscillation, and you need to remember that during one complete oscillation, the kinetic energy will be a maximum twice. This means that looking at this graph, the time period can be read as being 0.84 seconds at this point here. So starting from minimum kinetic energy at the amplitude when it's released, minimum again at the opposite side, and minimum back in the original position. This gives you the time period, and the reciprocal of this leads you to the frequency. Finally, consider a sensible number of significant figures having read time from the graph. Next, you're asked to sketch on the graph how the potential energy of the mass varies with time. And you're asked to cover the first second of the oscillation. So my answer is shown as the blue graph here. Remember that the kinetic and potential energies must always add up to the same total. So when the kinetic energy is 0, the potential energy will be a maximum, and vice versa, and they always add up to a total of 0.1. In the mark scheme, the points that I've marked here are what would be checked. So checking the maxima and minima, the inverse shape, and also that the two lines cross at the same value for energy on the y-axis. Now we move on to part B, a completely different scenario and a lot of information given both in the text and in the diagram. So take time to consider everything that you have been shown. So we have a ride called a jungle swing, and reading the text, the harness has got 3 riders strapped to it, and it's supported by 4 steel cables. An advert for the ride states that the riders will be released from a height of 45 metres, as shown here, and they swing with a period of 14 seconds. At their lowest point, they are 1 metre above the ground, and they travel at speeds up to 120 kilometres per hour. So, first part of the question, you're asked to treat the ride as a simple pendulum and to show that the distance between the pivot and the centre of mass of the riders is about 49 metres. So that is this distance here in the diagram. So using the time period that you've been given and the equation for the time period of a pendulum, we want to substitute values and ultimately find the value for the length. So here you can see I have rearranged the equation first of all, and then I have substituted in the values given. So g just comes from the datasheet, 4 pi squared is a constant. I'm only actually bringing the value of 14 in from the text. This gives me an answer of 48.7, consistent with the value given. Note it is good to give your own answer to one extra significant figure when trying to prove a point like this. Next, you're told that the riders and their harness have a total mass of 280 kilograms. You are asked to calculate the tension in each cable at the lowest point of the ride. You are told that you may assume that the riders pass through this point at 120 kilometers per hour. You can also assume negligible mass of the cables and that the cables are vertical at this point. A quick glance and you see that there are 4 marks allocated, so you can expect this to be quite an involved calculation. So look very carefully at information given. First of all, the speed has been given in kilometers per hour. This is not a standard unit, so you need to convert it to meters per second. So we have 120 kilometers multiplied by 1,000 to get it into meters. And on the bottom line here, we are converting 1 hour into seconds. That leads us to an answer of 33.33 meters per second. I'm keeping one extra significant figure to carry through my calculation, and then I'll make a decision at the end what is appropriate. Next, I know that I've been asked to calculate a tension. That would get me thinking about the forces involved in this situation. I might next decide to work out the centripetal force. I know this is a circular motion question. The swing, part of the swing, is a circular path. So simply F equals mv squared divided by r, substituting in the given mass, my calculated speed, and the radius from the previous part of the question. This gives me a value for the centripetal force. I now need to consider the overall situation a little bit more closely. I've drawn a diagram here to consider the forces acting on the swing when it's in its lowest position. So I have shown the weight of the riders, and I've shown the tension in the cables. The centripetal force is provided by the resultant of these two forces. I know the centripetal force acts towards the centre of the circle, towards the pivot. And so the resultant force must be the tension minus the weight. This equals the centripetal force. So to find the tension, I have to add the weight to the previously calculated centripetal force. So here you have my previous answer plus the values for m times g. Now, one final step. Having found the tension in the cables, I need to be aware that I want the tension in each cable. 4 cables were sharing this force, so the final step is simply to divide by 4 and consider an appropriate number of significant figures. Zeros are always a little bit ambiguous, but I'm erring on the side of caution and keeping with 3 significant figures. Next part of the question asks us to show that the maximum speed in the advert is an exaggerated claim. We can assume the riders are released from rest, and we can ignore any effects of air resistance. So this is an energy conversion scenario. So the gravitational potential energy at the top of the swing is equal to the kinetic energy at the bottom. This is because we're ignoring any losses. You can cancel the mass, simplifying the calculation. So we just have g the gravitational field strength times the height. This is the height fallen by the swing, so I have subtracted the 1 metre from the 45 metres as shown in the diagram. This is equal to a half times the speed squared. So rearranging and substituting values leads me to an answer of 29.4 metres per second. This was a show that question, so you do need to follow through with a statement to comment that this value is less than the value of 33 metres per second that we calculated in the previous part. Alternatively, you could convert 29.4 metres per second to kilometres per hour and compare that with the value of 120. Finally, you are told that the riders lose 50% of energy of the oscillation during each half oscillation. After one swing, the speed of the riders passing through the lowest point is 20 metres per second. You're asked to find the speed when they pass through the lowest point, travelling in the same direction after 2 further complete oscillations. You have to read and think carefully to get this question correct. It's referring to half oscillations here and complete oscillations here. So 2 further complete oscillations means 4 further half oscillations. So it's going to lose 50% 4 times. That's going to lead to a 1/16 of the kinetic energy left. Then, using the equation for kinetic energy, you can look at the variables. If the kinetic energy is going to be 16 times smaller, then the speed would be 4 times smaller, because when you square it, that would then lead to the factor of 16 required. So simply divide the speed that was given, 20, by 4 to give 5 metres per second. I've shown an alternative approach here as well. You could calculate a value for a 1/16 of the original kinetic energy. So here we have a 1/16 of a half mv squared. This gives the final value for the kinetic energy, and you can from that then calculate the velocity.